Ever found your computer just, grinding to a halt when you throw a massive spreadsheet at it? Or maybe millions of sensor readings?
Yeah, it happens all the time.
Imagine trying to analyze every single flight taken in a year. Or processing data from a global network of devices as it happens. Your single machine just, it can't handle that kind of scale.
Nope, not a chance.
So today, we're doing a deep dive into Apache Spark. It's this really powerful engine that, well, it turns those seemingly impossible data tasks into something efficient, something insightful.
Exactly.
Our mission here is to really distill the core ideas and capabilities, mostly drawing from the definitive guide, Spark the definitive guide, plus some other insights. We want to give you a clear understanding of its power without, getting totally bogged down in every single technical detail.
Precisely. Think of it as a shortcut to understanding how big data is really handled in practice. We'll explore its basic architecture, how it intelligently manages and transforms data, and yeah, some of the incredible things you can actually build with it.
Like what kind of things?
Oh, everything from real-time analytics dashboards to cutting-edge machine learning models. It's all about getting to those aha moments much, much faster when you're dealing with huge data sets.
Okay, so let's unpack this. If you're wrestling with just mountains of data, where does Spark even begin to simplify things?
Well, the first major shift, and it's a huge one, is that Spark doesn't work on just one computer. That's the fundamental difference.
Right. Not just my laptop.
Exactly. Instead, it uses what's called a cluster. Essentially, It's a team of computers, right?
Yeah.
All pooling their processing power, their memory. And Spark acts as the conductor of this whole orchestra. It coordinates and executes all the tasks across these machines working together.
Like going from a single violin struggling to a full symphony.
That's a great analogy, yeah. Now, managing this cluster, making sure the machines are ready, that's the job of something called a cluster manager. Pretty straightforward.
Okay.
But your application, the actual code you write, that has two really vital components running within this cluster setup.
And these are like the brain and the muscle you mentioned.
Exactly right. First, you have the driver process. That's the brain. It runs your main program, your main function. It keeps track of the application's progress, responds to what you tell it to do, and most importantly, it analyzes your instructions, breaks them down, and then schedules the individual tasks out to the workers.
So it's the coordinator. Absolutely essential.
Totally essential. Without the driver, nothing happens. Then you have the executor processes. These are the muscle. They live on the different machines in your cluster, the worker nodes, and they actually do the work on the data.
The heavy lifting, filtering, calculating, all that stuff.
All that heavy lifting, yeah.
Yeah.
Across all the machines in parallel.
And the real magic here, it feels like it isn't just about speed, though that's part of it. It's about sheer scale, right?
Absolutely. Your laptop, even a powerful one, it just hits a wall with truly enormous data sets. We're talking petabytes sometimes. Distributing that workload across a cluster isn't just faster. Often, it's literally the only way you can possibly process that much information effectively.
Okay, so we've got this distributed team of machines, this cluster, but how do we actually tell them what to do with all that data? That feels like the next big piece.
Right. How do you instruct this orchestra?
Yeah.
That's where Spark's structured APIs come into play. And the most fundamental concept there is arguably the data frame.
Data frame. Okay, I've heard that term. What is it exactly?
Think of it as a distributed table. It has rows. It has named columns, much like a spreadsheet you'd use in Excel or Google Sheets. But the key difference is that this table can be spread across potentially thousands of computers. It's designed from the ground up for massive scale.
Okay.
And every data frame has a schema. That's like its blueprint, It defines all the columns and what type of data is in each one, numbers, text, dates, whatever.
Makes sense, like defining table columns in a database.
Pretty much. But here's a really crucial difference from a regular spreadsheet or even many database tables. Data frames in Spark are immutable.
Immutable, meaning you can't change them.
Exactly. Once a data frame is created, you cannot change it directly.
So wait, if I can't change it, how do I actually work with the data? How do I filter it or add columns or anything?
Good question. To change a data frame, you define what are called transformations. These aren't changes to the original data. They are instructions for Spark on how to take an existing data frame and create a new, modified one.
Okay. So you chain transformations together.
Precisely. For example, if you have a data frame of numbers, like myRange, and you only want the even ones, you'd apply a where transformation, maybe something like myRange.where number %2 equals 0. This doesn't change my range. It defines a new data frame containing only the even numbers.
Got it. And you mentioned these are lazy. What does that mean?
Yeah, transformations are lazy. When you define one, Spark doesn't immediately go off and compute the result. It doesn't return anything right away.
Yeah.
Instead, it just takes note of the instruction. It builds up this internal logical plan. Basically, a recipe of all the transformations you've asked for.
Okay, so it waits. Until when?
Until you call an action. An action is what actually triggers the computation. Things like show to display a few rows on your screen, or count to get the total number of rows, or collect to bring the results back to your main driver program. Then Spark looks at the whole plan it built, optimizes it, and executes the work across the cluster.
This lazy evaluation, it
Well,
sounds like more than just a technical detail. It sounds really powerful.
Oh, absolutely. This lazy evaluation is like a superpower. Imagine telling a master chef, okay, I want this complex 12-course meal.
Yeah.
And you list out all the steps vaguely.
Right.
The chef, before even touching an ingredient, mentally figures out the absolute best way to prep everything, the optimal cooking order, the timing. That's what Spark's Catalyst Optimizer does with your transformations. It analyzes the entire sequence of operations before executing anything.
And that leads to big performance gains, I assume?
Huge gains, especially for complex queries on massive data sets. It can literally save hours, maybe even days of processing time compared to executing step by step. And what's really cool is whether you write your logic using these data frame operations like where or select, or you write standard SQL queries.
You can use SQL directly.
Oh yeah, Spark has excellent SQL support. But the point is, Spark's optimizer is so good that it often compiles both the data frame operations and the equivalent SQL query down to the exact same highly efficient underlying execution plan.
Wow. So you can just choose whichever way feels more natural to express your logic.
Exactly. Focus on the business logic, not on micro-optimizing the low-level execution. Spark handles a lot of that for you.
Okay, so Spark optimizes the plan. How does it then physically break down that work and run it across all those machines in the cluster?
Good question. To get that parallelism, Spark divides your data frame into smaller, manageable chunks. These are called partitions.
Partitions, okay.
Each partition is basically a collection of rows that sits on one physical machine in your cluster. This allows multiple executors, the muscle processes, to work on different pieces of your data all at the same time.
Parallel processing.
Exactly. Now, when we talk about those transformations, we can classify them based on how they affect these partitions. Some transformations are narrow. Narrow transformations are efficient. Think of something like a where filter. Each input partition, the chunk of data going in, contributes to only one output partition. The machine processing partition A only needs data from partition A to produce its result.
So each machine can work independently on its own slice of data.
Right. Spark can often pipeline these narrow transformations together, performing multiple steps in memory without needing to rate intermediate results, which is super fast.
Okay, that sounds good. What's the alternative?
The alternative is wide transformations, often called shuffles. This is where things get more complex and potentially slower.
Shuffles. Sounds like shuffling cards.
Kind of. It happens when input partitions contribute to many output partitions. Think about sorting the entire data set. To figure out the final sorted order, a machine working on one output partition might need data from all the original input partitions.
Ah, so data needs to move between machines.
Exactly. Data has to be exchanged across the network. Machines need to talk to each other, send data back and forth, and often write intermediate results to disk. This whole process is the shuffle.
And that's the bottleneck you mentioned earlier.
It's a very common performance bottleneck, yes. Operations like sort, group B, to aggregate data by key, or joining large data sets usually involve a shuffle. Identifying and minimizing or optimizing these shuffles is a key part of tuning Spark jobs.
Okay, that makes sense. Now, data isn't always just sitting there in files, right? What if you need to react to data as it arrives, like in real time? And what about all the excitement around machine learning? Can Spark handle that too?
Absolutely. Spark is incredibly versatile. It's not just for static batch processing. It has a powerful component called structured streaming.
Structured streaming, okay.
This API lets you apply the exact same data frame operations we've been talking about, filters, selections, aggregations, but on continuous streams of data. It processes the data incrementally as it arrives.
Incrementally?
Yeah.
So it's not reprocessing everything constantly.
Precisely. Imagine getting logs every second. Instead of rescanning the entire day's worth of logs every minute to update a dashboard, structured streaming just processes the new data that has arrived since the last check. It's incredibly efficient for low-latency, continuous updating.
That sounds perfect for things like monitoring systems or fraud detection.
Exactly. And it handles tricky real-world issues too, like event time versus processing time. Event time is when the thing actually happened out in the world, recorded in the data itself. Processing time is just when Spark sees the data.
And those can be different, right? Data might arrive late.
Very often, yeah.
Yeah.
Especially in distributed systems. Structured streaming lets you work with event time, which is crucial for accurate analysis when dealing with late or out-of-order data. It uses features like watermarks to manage this, basically saying, okay, I'll wait a certain amount of time for late data, but after that, I'll proceed with what I have.
Smart. And how do you get the results out?
You have different output modes. You can append only the new results, update existing results if they've changed, or do a complete rewrite of the output table each time. The mode you can use depends on the type of query and where you're sending the results.
So if I'm building, say, a system to analyze sensor data live or detect fraudulent transactions as they happen, I can use the same data frame language and tools I used for my historical batch analysis.
Exactly the same tools and APIs. That unification is a massive advantage. And this consistency leads us right into another powerful component, MLlib.
MLlib, the machine learning library.
Right. Spark's built-in machine learning library. It's comprehensive. It offers tools for classification, regression, clustering, building recommendation engines, even graph analytics, all designed to work at scale on distributed data within Spark.
And it uses those data frames we talked about.
Yes, the primary focus for MLlib now is the higher-level data frame API. There's an older RDD-based API, but it's mostly in maintenance mode. Using data frames makes integrating ML into your existing data pipelines much smoother.
So how does it simplify building these complex models? Is there a standard workflow?
There is. MLlib heavily promotes the use of pipelines. Think of a pipeline as a standardized assembly line for your entire ML task, from raw data to trained model.
An assembly line? Made of what?
It's made of stages, two main types, transformers and estimators. Transformers are steps that take a data frame and produce a new data frame, usually by adding, removing, or modifying columns. This is where most feature engineering happens.
Feature engineering, turning raw data into something the algorithm can understand?
Exactly. Like converting text categories into numerical indices using string indexer. Then maybe turning those indices into binary vectors with one hot encoder so the algorithm doesn't assume an ordering. Or combining multiple feature columns into a single vector column using vector assembler, which is what most ML algorithms in Spark expect as input.
Okay, so transformers prepare the data. What about estimators?
Estimators are the actual learning algorithms. They take a data frame and produce a transformer specifically, a trained model. For example, a logistic regression estimator learns from the data and produces a logistic regression model, which is itself a transformer that can predict outcomes on new data.
Got it. And you mentioned text processing examples.
Yeah, for text, you might use a tokenizer to split sentences into words, then count vectorizer or hashing TF to turn those words into numerical counts, and maybe IDF, inverse document frequency, to weight the importance of words. These are all transformers you'd put in your pipeline.
And what about something like clustering? Finding groups in data.
Sure. A classic example is k-means clustering. It's an unsupervised algorithm, meaning it doesn't need pre-labeled data. You tell it how many clusters K you want to find, and the k-means estimator iteratively assigns data points to the nearest cluster center until it finds stable groupings in your data. It's great for discovering hidden patterns.
This all sounds very powerful, but it raises an important practical question. When we're actually down in the weeds, working with the data day to day, what are some key things to know about manipulating different data types? And what happens if Spark's huge set of built-in tools still doesn't do exactly what I need?
That's a really great practical point.
Yeah.
Let's dive into some of that nitty-gritty. Spark gives you a very rich set of built-in functions, optimized to work efficiently across the cluster for almost every common data type.
Like numbers and text.
Exactly. For numbers, you've got everything from basic math and rounding, including different rounding modes like round for half to even, to calculating summary statistics like mean, standard deviation, min, max, count. You can even compute correlations between columns easily.
And strings. Text data is often messy.
Oh yeah, Spark has a ton of string functions. Changing case, lower, upper, init cap, trimming white space, trim, ultra, margin, padding strings, LPAD, RPAD, and really powerful tools using regular expressions like regex replace to find and substitute patterns, and regex extract to pull out specific pieces of text that match a pattern.
Dates and times always seem tricky. How does Spark handle those?
They are tricky. Spark provides functions like toDate to convert strings into proper date types, date diff to find the number of days between two dates, months between for timestamps, and so on. But here's that critical warning again. If Spark tries to parse a date string and fails, maybe the format is wrong. It will not throw an error by default.
It just returns null, silently.
It silently returns null, which can be a nightmare to debug later in a complex pipeline if you're not expecting it. You really need to be careful with date parsing and potentially add checks.
Okay, that's a huge heads up. What about handling nulls in general? You mentioned that nullable flag in the schema isn't strict enforcement.
Right, it's more of an optimization hint for Spark. If your data unexpectedly contains nulls in a column you declared as non-nullable, things might break or give wrong answers downstream. You must proactively decide how to handle nulls yourself.
What are the options?
You can explicitly drop rows containing nulls, either any null or nulls in specific columns. You can fill nulls with a specific value, maybe 0 for numbers, or an empty string, or a global default. Or you can use the coalesce function, which is really useful. It takes a list of columns and returns the first non-null value it finds in that list for each row. There's also equal safe for comparing values when one or both might be null.
Okay, lots of tools there. What about more complex data structures within a data frame, like lists or nested objects?
Spark handles those too. It supports structs, which are essentially like data frames nested inside a data frame cell. It supports arrays. You can create them using functions like split to turn a delimited string into an array, and access elements using familiar indexing like array_0. And it supports maps, key value pairs. Spark even has functions like toJSON and fromJSON to easily convert these complex types to and from JSON strings within your data frame.
All right, that covers a lot of ground with built-in stuff. But back to my earlier question. What if none of these quite fit? What if I have some really specific custom logic I need to apply?
That's where user-defined functions, or UDFs, come in. You can write your own custom functions and register them with Spark to use in your data frame operations or SQL queries.
Okay, so I can write my own Python or Scala code.
You can. But, and this is a big but, you need to be really aware of the performance implications.
What's the catch?
If you write a UDF in Scala or Java, it runs directly within Spark's core engine, the Java Virtual Machine, JVM. That's generally pretty fast. However, if you write a Python UDF, things get more complicated under the hood.
How so?
For each worker node processing data, Spark has to actually start a separate Python process.
Yeah.
Then, for every row, or batch of rows, it has to serialize the necessary data out of the JVM, send it over to the Python process, execute your Python function there, get the result back, and serialize that result back into the JVM.
Whoa, that sounds like a lot of overhead, sending data back and forth between
So
processes.
that is a lot of overhead. That serialization and inter-process communication can become a major bottleneck, especially if your UDF is doing something simple that could have been done with built-ins, or if you're processing billions of rows.
So the practical advice here is?
The key takeaway is definitely, always try to achieve your goal using Spark's built-in functions first. They are highly optimized to run efficiently within the JVM and directly on Spark's internal data representation. Only resort to UDFs, especially Python UDFs, when the logic is truly custom and cannot be expressed using the standard toolkit. And if you do use them, be mindful of their performance cost.
That makes perfect sense. Prioritize built-ins, use UDFs sparingly. Okay, so once you've built your Spark application using data frames, maybe some streaming, maybe MLlib, how do you make sure it actually runs efficiently and reliably? Especially when you scale up, it's not just about getting it to work, right? It's about getting it to work well.
Absolutely. Performance tuning and monitoring are critical, especially for large-scale production applications. And you actually have a lot of control through your code choices and various configurations.
Like how you store the data.
Exactly. For data at rest, before Spark even reads it, storing it in efficient, binary, column-oriented formats, like Apache Parquet, is almost always recommended. Parquet allows Spark to read only the specific columns needed for a query, which can be a massive I/O saving.
And you mentioned partitioning before.
Yes. Proactively partitioning your data when you write it out is huge. This means organizing your data into folders based on the values in one or more columns, like year and month. If your query filters by year and month, Spark can completely skip reading data from all the other folders. Bucketing is a similar concept, pre-shuffling data based on a key column to optimize joins or aggregations later.
Smart. What about optimizing the actual processing?
Well, we touched on parallelism, making sure you have enough tasks running concurrently to utilize your cluster hardware. Often aiming for 2-3 tasks per CPU core is a good starting point. Tuning the number of shuffle partitions, spark.sql.shuffle.partitions, is key for those wide transformations. And if you have data frames or RDDs that you access multiple times, maybe in an iterative machine learning algorithm, or if you branch your logic caching or persisting them in memory or on disk, can save Spark from having to recompute them from scratch every time.
Catching avoids rework. Makes sense.
Definitely. Another useful tool is broadcast variables. If you have a relatively large lookup table or maybe a trained ML model that every task needs to access, broadcasting sends just one read-only copy to each worker node instead of packaging it up and sending it with every single task, which saves a lot of network traffic.
Ah, efficient distribution of shared data.
Precisely. And fundamentally, just using the structured API's data frames and datasets helps a lot. They allow Spark to manage memory much more efficiently by working with its internal optimized format, Tungsten, reducing the overhead of creating Java objects and the pressure on the garbage collector compared to the older RDD API.
Okay, so lots of tuning options, but how do you know what to tune? Monitoring sounds like the key there, like an early warning system.
It absolutely is. The Spark UI, user interface, is your indispensable window into what's actually happening inside your running application. It's a web interface, usually accessible through the cluster manager.
What does it show you?
It breaks down your application into jobs, stages, sets of tasks separated by shuffles, and individual tasks. You can see how long each stage and task took, how much data was read or written, shuffle statistics, details about your executors, and even the execution plan for your SQL queries. It's invaluable for debugging and finding performance bottlenecks.
So if something is slow, the UI is the first place to look.
Definitely. For instance, you might notice that one or two tasks within a stage are taking way longer than all the others. That's a classic sign of data skew.
Skew, meaning the work isn't distributed evenly.
Exactly. Some partitions might have vastly more data than others, causing the tasks processing them to lag behind. The UI helps you pinpoint where the skew is happening.
And what about crashes, like running out of memory?
Yeah, out-of-memory OOM errors are another common issue, especially as data scales. The UI and executor logs will tell you if it was the driver process or an executor process that ran out of memory.
So when things do go wrong, what are some of the most common culprits and fixes?
Well, sometimes jobs just don't start. That could be cluster resource issues, maybe not enough memory or CPU available, or network problems preventing the driver from talking to executors, or even just misconfigurations in your job submission.
Okay. And for the slow tasks or skew you mentioned?
For slow tasks or skew, identifying it in the UI is step one. Remedies often involve increasing the number of partitions, repartition or coalesce, sometimes adding a random key to spread data more evenly before a group by called salting, or just making sure you push filters and column selections where in select before expensive operations like joins or aggregations to reduce the amount of data being shuffled.
Reduce the data early. Smart. And the out-of-memory errors.
For out-of-memory errors, the simplest fix is often just to allocate more memory to the driver memory, or executor memory. For Python users specifically, a very common cause of driver OMs is trying to collect too much data back from the cluster into a single Python variable. The conversion process in the JVM can blow up memory, so be careful how much data you pull back to the driver.
Good tips. And beyond Spark's core, it feels like there's this whole universe of other tools and libraries built around it, right?
Oh, absolutely. The Spark ecosystem is massive and incredibly vibrant. There's a site called Spark Packages, spark-packages.org, which lists hundreds of community-contributed libraries that plug into Spark.
For doing specialized things.
Yeah, anything you can imagine. Connectors for different data sources, advanced algorithms, visualization tools, domain-specific libraries, and critically, there are the language-specific integrations. PySpark makes Spark feel very natural for Python developers.
Which is huge, given Python's popularity in data science.
Definitely. And for R users, you have both Spark R, which tries to closely mirror the core Spark API, and Spark Lear, which offers an interface that might feel more familiar to R users, particularly those coming from the deployer world. They offer different philosophies, but both provide powerful ways for R developers to leverage Spark.
So lots of ways to plug into Spark, regardless of your preferred language.
Right. It really lowers the barrier to entry for distributed computing.
Wow. Okay, we have covered so much ground today. It's really quite a journey from just understanding why you need distributed computing in the first place, all the way to building real-time machine learning models and then fine-tuning their performance. Spark truly feels like a definitive tool for tackling these big data challenges. For you, thinking about everything we discussed, what really stands out about Spark's approach?
If I had to connect it all to the bigger picture, I think it's Spark's unified approach. The fact that you can use essentially the same core concepts, data frames, transformations, actions for batch processing, for real-time streaming, and for large-scale machine learning is incredibly powerful.
One toolkit for many jobs.
Exactly. And its ability to optimize your logic effectively, whether you write it as data frame code or SQL, across different languages like Python, Scala, Java, or Spark. It means you, the developer or data scientist, can spend less time worrying about integrating a bunch of disparate complex systems and more time actually focusing on solving your data problems. It lowers the friction significantly.
That's a fantastic point. It really democratizes access to this kind of powerful computation. So thinking about that unified power and just the sheer ever-increasing volume of data being generated constantly, what's maybe a provocative thought we can leave our listeners with to mull over?
Okay. How about this? In a world generating data at this relentless pace, how does a tool like Apache Spark fundamentally change not just what analyses become possible on massive data sets, but perhaps more importantly, how quickly can we actually translate that raw data into actionable insights, into continuous intelligence that drives real-time decisions for complex real-world problems? Is the bottleneck shifting from computation to interpretation?
Ooh, that's definitely something to chew on. Shifting the bottleneck. I like that. Well, hopefully this deep dive gives everyone a solid foundation to explore those questions further. Until next time, stay curious.